Thank you, Jack. So we come to our final day, and that means our final keynote. I know, it's very sad that everyone we've had doing keynotes and everyone else speaking this week have been absolutely fantastic. I look forward to catching up on that next week. So our final keynote for the week is Jess Frizzell. She knows a couple of things about containers. She has been a maintainer for Docker. She has contributed to Golang, Run C, and a couple of other projects around the place. She currently works at Microsoft and has also worked at Google and a few other largish organizations. We're very pleased that she was able to make it here, and please welcome Jess Frizzell.
Thanks for having me here. This is actually a bit unreal. The whole container craze has been a little bit unreal, but yeah, it's super awesome to be here. This conference has been amazingly fun the entire week. So I'm going to be talking about containers from user space. Mostly where I live is user space. I'm not sure if any of you are familiar with the movie Plan 9 from Outer Space, but it's a terrible movie. And actually Plan 9, the OS, I think is based off that name. But this is going to be containers from user space, so we can only hope that it's so bad that it's good, this talk, just like the movie. Yeah. So who am I? I work at Microsoft. Selling out has been amazing. If you have any questions about that, I'm happy to answer them. I work on open source and containers, and specifically now on Kubernetes. I kind of live between the layers of abstraction, and I really like it there because it's fun. And I get a joy from pulling features out of one layer and into the other. So this talk is going to be a lot about how we took features from the kernel, made containers, and then pulling them back into Kubernetes and orchestrators as well. So I'm going to cover a lot of things, but we're going to run through a lot of them very fast because I think people kind of have some pre-existing knowledge here. So I'm going to go over what are containers, and then a little bit of Linux container history because Docker obviously wasn't the first, and we didn't even come up with the container name. It was already there. Are containers secure? And then, is it the year of Linux containers on the desktop? And then a bunch of experiments kind of outside containers that relate so that I'm not just containers, because that's intense. And then the future is kind of where we're going to spend a lot of the time. Everything else is kind of just a very brief touch on it. Sweet. So we'll start with what is a container? Because I think there's some confusion. It's not a real thing. They're made up of Linux primitives, mostly the differences between zones, jails, and VMs. A lot of people will ask me this, and I think it's because they're trying to get me all riled up, or they think that I love containers the most. Actually, I love zones first. So, and if you never read the zone design doc, it's a great read. It's really cool. But zones, jails, and VMs are all first-class concepts. And then containers are made up of C groups, namespaces, LSMs, and blah, blah, blah. There's a bunch. We'll go over it. So yeah, real things. And then there's not a real thing. So this is a feature and not a bug, and I'll also touch on that too. It's really cool what you can do since there are so many pieces that you can put together. But just real fast, namespaces control what a process can see, and there's a whole bunch of those. And then C groups control what a process can use. So this is where you get your resource management from, and there's a whole bunch of those too. So if we kind of just start from the very base of what I consider a container, it would be namespaces and C groups. So it looks like that. And then I took away the words, so just imagine they're still there. So on top of that, we actually layer a bunch of other things. So one of them is AppArmor, which is an LSM, and we have same defaults for that. So when you're running a Docker container, at least, you're getting these same defaults that I'm going to mention for all of these out of the box. So we prevent writing to obvious places where you would not want to write. Things in proc, things in sys. We also prevent mounting, which is also gated, obviously, by cap sysadmin, but it's nice to have an extra layer of protection. You never know. So another one would be SE Linux. You can't run these side by side currently, so they're both blue. But this is another LSM, and this one's label-based. So the defaults here are that Docker gets access to everything in user and Etsy, and then you can actually relabel content on the host to make it have access, or you can relabel things in user or Etsy to say, no, you can't have access. So setcomp is another cool one, and this is a feature that I worked on a lot in Docker. So these are syscall filters, so you can kind of define what is allowed and denied in a container. And what we have in Docker is a whitelist of syscalls that are allowed. And it took a really long time to kind of build this whitelist, because at the point where I was adding this feature, Docker was already like insanely popular. So the fear was that if we make a whitelist, like we're gonna break all the containers in the world by missing one syscall. I lost sleep for like weeks over it. And actually, like the day before the release, I was running Skype in a container, super normal. And that's a 32-bit application running on a 64-bit machine. So I realized that we were missing send and receive, like pretty common syscalls. So then I was like, oh my God, this is really scary. But in our testing phase, and Skype was obviously super uncommon, I went through all the public Docker files on GitHub, and I pulled them all, and I ran them on this huge cluster with the patches, and kind of collected all the EPERMs that were being thrown. And if they were like an EPERM that was bad, I would fix it. And then if it was one where it should have EPERMed, then it was fine. So that was kind of a cool way to test things. But yeah, so our whitelist just specifies what's allowed. And it blocks like a bunch of bad stuff, not limited to the following, but I'll like just touch on a few. So anything that is with the kernel keyring, it's not actually namespace yet, so we just don't allow that. Clone, we have specific masks so that you cannot clone a new user namespace inside a container. And this is mostly just so that people don't get into those really weird situations where user namespaces allow you to kind of like escalate your privileges or, you know, break out. And all the other clone flags are gated by capsysadmin, which we don't allow in containers to begin with. And then same with unshare, we just don't allow people to create a new user namespace or unshare a new user namespace. So then there's no new privs, which is a Linux flag for fork, exec, and clone, and it prevents new privileges from being added to a process. So this one was cool in that in Kubernetes, we kind of reversed the naming. So it's like allow privilege escalation. So you're kind of implicitly denying privilege escalation, and then you have to say like, I would like privilege escalation, so then we don't add the flag. And then capabilities are super basic. These are the ones that we allow by default, and none of these are really all that bad. I wish we could get rid of capnet raw, but if people want to ping inside a container, you need it. So that kind of sucks. And I guess people ping inside containers. And so actually just a fun fact, not all these defaults carry to all the runtime. So Rocket and systemd and spawn, they actually add cap sysadmin to all containers, which I have an issue with. But yeah, I just think it's a bit unnecessary. So yeah, that's what a container is. It's just made up of all these parts with all this other stuff on top. You can kind of consider it just like a bunch of duct tape. But then what about those like Intel Clear containers, which are now formerly known as Kata containers? Those are actually VMs, right? It's KVM and QEMU. They're like these really cool fast booting containers. But they call them, well, they're fast booting VMs, but they call them containers. Like, I'm not really sure what is happening there, actually. I don't know if it's container, mostly because it is actually a virtual machine. Like, I definitely like it, though, because from a technical perspective, it's really cool what they're doing. Crazy fast booting VMs, like I would totally use those all the time, and I do. I'm actually on their technical architecture board, too. But yeah, they're really cool if you've never played with them. I personally would have called them glass houses, though. I don't know, it seemed more fitting. naming things is super hard. Obviously, it's like one of the hardest problems in computer science. I mean, we could have just called them all boxes instead of containers. I mean, who knows? It could have been called like anything that was possible, and then we would have been having this like whole box fad. We could have even said little boxes on the hillside, like in Weeds, and everyone would have gotten that like song stuck in their head, and it would have been really funny, instead of like all these like Tupperware jokes. So yeah. So the history of Linux containers is kind of cool because they've been around a long time, like way before Docker. And Docker kind of just, I guess, made it more usable, or maybe it was all the hype around Docker that people got like really excited about it. So this is going to be the history of containers that use the Linux primitives, not to be confused with the glasshouse ones that are actually VMs. So there was OpenVZ, which was 12 years ago. And I'm not actually sure if that's still maintained, but I think people still use it. So that's a really long time ago. And even before that, I think, was when Google added C groups to the kernel. I meant to put that data in here and then I forgot. But then after that, shortly, was Linux vServer, which I do not think is still maintained because I haven't heard about it in a long time. Then LXC was 9 years ago, and this was actually my first kind of interaction with containers. And I think that if anyone is to assign blame for the whole container wording, it would be LXC. But don't tell them I said that. But yeah, I mean, LXC stands for literally Linux containers. So LXC was cool. Like, I ran in production a cluster of a bunch of LXC containers, and then when Docker was showed at PyCon, when they first showed kind of what Docker was, even though it didn't necessarily work like it did today there, I switched over our environment to be Docker. And that was pre 1.0, and there was a bunch of bugs, and that's kind of how I started contributing and stuff. But yeah, so Docker's initial release was almost 5 years ago, and initially, even in that PyCon demo and stuff, the backend was LXC. And we carried that as a backend option for a long time, but it was replaced as the default backend pre 1.0 in v0.7. And I do remember when we were using Docker at that time for this production cluster, it started working a lot better, mostly because it's really hard to kind of write code on top of other people's binaries when you're just executing arbitrary binaries. It's not like there was an API, you're just execing another binary. So kind of capturing, the output there is hard to have good debugging. But yeah, that backend was carried into Docker 1.4 when I think we finally killed it. It was hard to maintain. So then there was also let me contain that for you. And this was right around the same time as Docker, if you look. And I really liked actually the name of this project. I still think that's super dope name, let me contain that for you. And this was by a bunch of Google people. And then they started contributing to libcontainer, which was Docker's Go library that replaced the LXC backend. And I remember on my first day at Docker, we actually met with these guys. And it was really cool because I was oh, they're let me contain that for you. And they have this really cool project. And this was definitely before I think containers were cool. And then there was Rocket, which is CoreOS's kind of container runtime. And this was what I would like to say was the start of the container wars. But there's a bit more on that later. Are the container wars over? I don't know. So runC came as trying to end the container wars. And this was donated to a foundation, which is spawned as a child foundation, I guess, of Linux Foundation. So it's the Open Container Initiative. So it was kind of just we'll give this away so that everyone stops, saying that we're, only having the best interests of Docker, which is good. There should be governance around this if it's going to be this huge world of containers. So yeah. runC is really cool, and that project is really cool if you're interested in helping out. So container runtimes are kind of like the new JavaScript frameworks. There's so many, and if I went over them all, we'd be here all day. But that's kind of the base frame of what containers are and where they started from. So moving on to our next topic, are containers secure? I get this a lot, and even in the beginning days of Docker, there was like so much shade thrown, which like, yes, was very, it made sense then, but then after we started adding all those layers of LSMs and seccomp and stuff, it kind of changed the story. So yes, they definitely are secure, and I can prove it, and we're gonna do that right now. So I like to think about containers kind of as Legos. Okay, so people get mad whenever I add the S there, so just deal with it. Like, I put the S in parentheses, and I can't just like stop a habit, okay? So VMs, zones, and jails, they're all like, if you bought the Legos, already put together and glued, which is no fun, by the way. But yeah, so you kind of just already get this like artwork in the form of pieces, but it's already glued. So you can't take it apart or anything. It's not really all that cool. They're the Death Star. Like, you don't have to do any work. It's just there. They come pre-assembled out of the box, right? So containers, they just come with the pieces. And like the box says, you know, build the Death Star. But you're not tied to building the Death Star. You have all the pieces. You could put them together in any way you want, right? Like, you could build a boat. Like, you are the master builder here. You can do whatever you want, which is really cool. Like, you could even do this, where you don't have the pieces for the right thing, but you build it, which is a little backwards, but cool. So you can turn on and off certain namespaces, which is super dope. So like, say that you want to have, you know, better networking, like lower latency, and you have like all these patches for your kernel for really, really low latency. Think like stock trading, right? So if you just run in the host namespace, that's kind of how we call it, even though it's just host networking and we don't turn on the network namespace, then you can actually just use all those low latency kind of network features that you had. And you can do the same for like all the other namespaces as well, which is really cool. You can also share namespaces between containers. And this is actually the part that I really love, because, and I've showed this like in numerous other talks. Okay, so what I like to do is, say like an application is behaving poorly in a container, and I want to like strace it, right? So you could like strace it from your host, like the actual PID of the thing running in the container, obviously. But like, where's the fun in that when you could share the PID namespace and then run strace in a container? Which is kind of cool. And then also you can do the same with like network namespaces. So say application misbehaving and you want to start looking at all the packets, right? So you can run like Wireshark or something like that in a container with a shared network namespace, and debug that container. And it's just really cool, the combinations you can get into, and a lot of people have like really crazy things that they've done with this. And like one of the most common use cases that people don't necessarily know about, but Kubernetes, when you're spinning up these pods that they have, which is just a kind of grouping of containers, they all share a PID and net namespace. And this is because the network one is for convenience, obviously. PID is so that they can send signals to the other things running in the pod, and also so that they can know like what is happening, which is really cool. So like, every Kubernetes pod actually starts as this pause container, which kind of just sets up these namespaces. Then they're all spawned from there. So everything is a tunable knob, which is really cool. But obviously you can like shoot yourself in the foot really easily when you start tuning these knobs in ways that you are like unfamiliar with, or you're not really sure what the consequences of these actions are. So that's why we made Docker with sane default, so that people don't do this. But you can also like even sandbox applications even further than like the Docker seccomp default profile and like the default, you know, AppArmor or SE Linux stuff. You can go like way beyond what we did. Mostly we did what we did because it had to work for 99% of the containers out there. So to pretty much stop people from ever annoying me about if containers were secure, I made this website called contained.af. And this was like almost 2 years ago now, but it's pretty cool. There's like this terminal. So first it was kind of just meant as a game, because I love like kind of teaching people from the standpoint of putting them into a weird environment and then being like, what do you have access to? What capabilities do you have? So it will ask you a series of questions like, do you have access to CapNet raw? So kind of like the thing you're supposed to do is try to ping And then when ping fails, you're like, no, I don't have access to CapNet raw. So there's a bunch of questions like that, but and it is kind of like a learning exercise, and it's pretty cool. And a lot of people have actually added questions. This is all open source on GitHub, so if you have cool things that you want to put in there, I would obviously merge it. But there's a hidden game here as well, in that like I obviously opened this terminal up to the world, and if you were to capture a flag that is actually on the underlying VM that is running these, you would have to break out the container to capture the flag, and then if you email me, then I will give you like ultimate praise for the rest of my entire life, because I don't have money to give away, but like I would definitely like make sure that everyone knew that you were the coolest person on earth. So yeah, there's like a flag with ASCII art on these VMs, and you know, a lot of people don't play the actual game that is like learning about containers and caps and stuff like that. They're just like, no, I want to capture the flag. So no one has managed to break out of the container, and it's not because they haven't tried. They've definitely tried. I've talked to like a lot of security researchers who have just tried putting, you know, the latest hip proof of concept of a vulnerability in there, and I'm like, that's not going to work. Like, you have to try harder than that. Like, obviously, anything that is just like off someone's, you know, script on GitHub is not going to work. I mean, I'm not obtuse. But yeah, so why is it that no one has actually been able to do it? Well, it's because I took the default SecComp profile and then I took a lot of things out of that. So basically, if you're going to have to kind of, you know, bypass this like first layer of security, you need to use something like ROP, which is return-oriented programming. So you'd have to gain control of the call stack and then execute machine instructions from memory there, which is a lot kind of similar to the stuff in Spectre where, you know, he calls BPF even though it's not enabled, which was really cool, by the way. So yeah, you'd have to do that, and no one's gonna waste their time, you know, writing return-oriented programming for my shitty web app. Like, it's just not worth the time, especially when all you get is my eternal praise. And I don't have anything on that machine that's cool other than this flag with ASCII art, which I assure you the ASCII art is more of a joke than anything cool. So it is totally a shitty web app. Like, I wrote the actual app itself in one day and then I never looked back. Like the container, it took a long time, but that was like years of work on Docker and stuff like that. But the app itself that is spinning up those terminals is really bad. There's probably race conditions galore. So what I tell all of them, like when these security researchers come to me, I'm like, you'd be better off attacking the app. But obviously, like, that's not as fun as like this terminal that you have in front of you. But even if you were to, you know, find some race condition, which I'm sure there's aplenty, you'd still be running in this container, you know, with at least the default SecComp filters. Like, I didn't really restrict them all that much further, but the default is really good. So they'd still have to then bypass that, which you'd need some sort of kernel O-day for. And I'm not sure anyone's gonna waste a kernel O-day on my stupid thing. And I update my kernels all the time, so yeah. So a sandbox is kind of defined as providing a net reduction in attack surface. And inside a container, less things are possible than on the host machine. So that is a sandbox. So containers are sandboxes as long as you are using these really nice defaults. So if you want to do all the same things that you can do on your hosts, like I personally use VMs for that, mostly because I love that containers are sandboxes and I don't really like you know, changing that. Or you could use, you know, a privileged container, which is what we named it, when you add all your devices and stuff like that. But just know, like, that's not a sandbox anymore because you just turned off all the like really nice security features that you got out of the box. So yeah, moving on. Containerizing the desktop, which is like one of my favorite things. So at first when I containerized my desktop, like I showed it at DockerCon like a few years ago, I used Docker for everything. Obviously it was DockerCon. So then I ended up switching everything to runc later on because Docker has this daemon, and I was just like, I really like super minimal, which is why I put everything into containers. Like, I hate when arbitrary files are on my host, or like I install a package from apt and then I don't know where all the files went. Like I know that I can look it up, obviously, but like it like hurts my soul for some reason because I'm like an insane neat freak. So I would not consider this for anyone else who is not like OCD about weird files on their host like I am. But yeah, so I ended up switching everything to run C, which was cool. And a lot of this was thanks to Alexa, who is here or has been at this conference all week. And he merged a patch to make run C have rootless containers, which took a really long time to merge, but it's awesome. So you can spawn containers as a non-privileged user, which obviously you could do with unshare when you unshare your user namespace and all this stuff. There was a lot of stuff that we were doing with containers that made this hard. But now it's easy. So previously I used Docker, so I had to like convert all my configs into these like run C OCI specs, right? It's just a JSON file. But I made this kind of tool, which works sometimes, works doesn't. So if you're actually going to use this, I'm sorry. I made a tool to do that, which was cool. And then as far as networking goes, because run C doesn't really provide any networking, it leaves it up to like a lot of other things. I made a tool for that too. So Docker has this like default bridge networking that kind of just works out of the box. So I basically just made a hook for run C that does the same thing. It sets up a bridge, it grabs an IP, then in the ultimate Unix way, it puts your IP in this file on your host so you can go look at it later or program around that. So that's pretty cool. So at that point on my computer, like I had sandboxed desktop applications running in containers, and none of them were running as root. So they were all rootless containers, and I had all the seccomp profiles around them, and so I felt like pretty great. Like my computer is clean. It's super nice. So then I started, at that point I was still using Debian as a base. I got a little bit OCD and I was like, I want even more minimal. Like I want to use one of these like hipster container Linuxes. And CoreOS is really cool, their container Linux, because it's based off Chrome OS. So all kind of the security things that you get from Chrome OS, you're also getting from CoreOS container Linux. So that would be like read-only user and then stateful read-write for the rest. So since it's a read-only user, you're like forced to use containers because you can't like just have arbitrary binaries on your host and execute them, right? So that's kind of cool because I was already doing that. I had everything running in containers. And you could also have auto updates. I'm not that insane yet. I've thought about it. I've started and then I've stopped. And then I've worked on actual work. So that's pretty much what's stopping me. But yeah, there are like a few projects that do like open source Omaha server things that I've been looking into, and like one of these days I'm gonna get around to doing it, and then I'll hate myself a little bit more for creating this really weird world for myself. The cool thing about like out of the box from CoreOS container Linux is that you can verify the integrity of the OS, and a lot of this work was done by Matthew Garrett, who is also here. So you get TVM support and DM Verity, which is super dope, so you can verify that like the root hash of your OS is right. And all I had to do was add graphics drivers to the OS. And since it's also based on Chrome OS, which is built from Gentoo, I just had to like emerge the world, which was hard in the beginning, but now I've gotten used to it. I actually also really like Gentoo. I don't think there's a Linux OS that I do not like. There's a lot of other OSs that I do not like. But Linux, I love them all. So this is kind of what it ends up looking like. You have your secure base, and then your containers with seccomp. It's just like this very pretty world, and everything's in little boxes. They're little boxes on the hillside. So yeah, it's been a lot about containers, so I thought I'd take a break to talk about something else cool. And then this all kind of ties together in the end in like a nice little bow. So all these kind of same like defaults that we applied to containers to make them secure and all that, that was just bringing up features from the kernel to user space, right? Like it wasn't novel at all. Like those things were already there, and you just have to figure out how to use them and then apply it to whatever you're doing. So like if you could almost do that with programming languages as well, it would be really cool. So as far as the layers of abstraction go here, it's just like kernel. programming languages. And like what it's exposing, the kernel obviously is system calls, and what programming languages are exposing is like the compiler and your standard lib. So the idea I had here was to take some Go code, and as you're compiling it, build out these seccomp filters based on the code itself for the binary, so that you're using, instead of using at like runtime, trying to figure out what you need and what to lock down, like you're doing it at build time based on the code. And Go is really good for this, and I'll explain why, because it made it insanely simple for me to add this. So why even generate seccomp filters at build time, right? Like you could probably, use ptrace, try to collect all the syscalls, all that stuff. I've heard literally every single way to do it from people, and people have built things, and I'm just not exactly sold on them. Mostly because like generating these security profiles and filters at runtime, it's been done in the past and it's failed, like over and over again. And it's not because of technical ability, like you can ptrace something, run unit tests and then collect all the things, right? But do your unit tests actually like cover 100% of your code? No. So like something's always missed, right? In this like profiling phase. So then everything breaks, and then the person's just like, I'm turning it off because I like just can't even live anymore. It broke everything. Like nobody ever really looks into the problem after that. They're just like, nope. So yeah, just as like to really drive the point home, it looks like this. Like a user will start profiling Chrome. They'll open some tabs, maybe do a few things, go on Facebook, whatever. And they're like, okay, that's good. I'm bored of this, right? Then you apply your generated profile or whatever, and you reopen Chrome like maybe weeks later, and you're doing something else. You're on YouTube or something, you're trying to play a video. And then like it's trying to use maybe a graphics driver or something that wasn't necessarily done before. And I'm not sure Chrome was the best example for this, but whatever, you get the point. So then everything stops working. They can't like, watch their YouTubes or whatever, and they're like, F this, I'm turning it off. So that's kind of like the problem that I have with runtime profiling, which is why I was like, build time, you can actually ensure all the code is included in the filter. Like even dead code, which we could rule out, like you could include that too if you want, which is kind of neat. At least you're like overkilling it versus underkilling it. So the Go compiler is really cool in that like instead of relying on something like libc or something for the syscalls, they just write the assembly for all the syscalls. And you can just look at this in the open source Go project under the syscall package. They have all this like generation of assembly. And you can just like see exactly how they're laid out. And actually the assembly for Go binaries, I think it looks pretty clean if you just look at it. And one of my coworkers and I are trying to write a disassembler, which will be cool. So if you hijack the part where it assembles the syscalls and just kind of collect them into an array or something, then you can get all the ones that you are using, and then you can then go ahead and apply that to a seccomp filter on run, which is cool. Then like your binary is basically only allowed to do the things it's supposed to. So yeah, that sounds really cool to begin with, but there are a few problems, obviously. So here's what happened when I tried this. There are like definitely 3 problems that I ran into, and some of them are minor and some of them are okay. So here's an example of Go code, which even if you don't know Go, you can probably read this. So I'm executing this random binary called my program. So I don't know what my program is gonna do, actually. That's already built, that's already a binary. So if I like lock down the syscalls for this Go app, like it's not gonna include the syscalls for my program, which really sucks. And that one's hard to solve, unless you did some sort of reversing of binaries, but that just goes down a really intense rabbit hole. So another one is Go just added support for plugins. The initial support for plugins is kind of meh. So people don't really use them, so this doesn't make that as much of a problem, as well as like the Go compiler actually builds the plugin, so we probably could add some sort of like seccomp header to them or something like that. So it's easily solvable, but still, if you're executing something else, almost like a DL open, it's hard to also get what that one's doing. So opening plugins was a sad point. And then this, so the syscall package in Go, you can obviously execute any sort of random syscall. So if you're passing in arguments to this like raw syscall and it's not like an actual syscall that we can parse, that's a problem because I don't know what it's going to be. And if it's up to even on runtime where you're passing it in through the command line, which this is a weird example, I don't know anyone who would ever do that. It's really up to the user as to what's going to be called, and there's really no way to solve that one. Which kind of sucks. But there are ways that I was even thinking of just if you see that one of these kind of circumstances is happening, you just turn it off entirely and stuff like that. But I also didn't feel like adding a bunch of code upstream and trying to get that in and doing the whole open source politics song and dance over this thing that didn't work perfectly. But it is cool, and I think that there's something here in that there will be better ways to do this in the future that do not have these problems necessarily, or there will be ways to solve these problems so that we can do this, because I think it would be dope. But yeah, right now it's just great. But Rome wasn't built in a day, so yeah, we could probably find ways. I'm still thinking about it. I'm definitely trying to make fetch happen, and that will be it. Yeah, so kind of another place where I saw to kind of put this same type of thinking of generating perfect filters is if we come back to our original layers of abstraction, right? My coworker, Brendan Burns, who is also one of the co-founders of Kubernetes to begin with, he just built another layer of abstraction on top of Kubernetes, and it's the standard library for cloud-native applications, and it's just running them on top of Kubernetes. So this is just a library that you can include in your code, and then it will self-deploy your code from the code itself. It's really cool. It's self-deploying binaries, if you think about it. But the cool thing is that library is in your code. So it's a cool kind of point where I think that we could also parse the syscalls and then create the perfect filter and then apply that to the orchestrator that is running in the background. So that's something I'm looking into, but yeah. So still trying to make fetch happen, just elsewhere. Yeah. Should be interesting. So some other crazy things, and I'll look into the future here, since we already have started talking about the future. I saw this paper from a little bit ago where they're running Linux containers in secure enclaves, so with Intel SGX. So a secure enclave is kind of an isolation of separate memory, and the threat model for secure enclaves and why you would want to use it, I think personally is for if you don't trust the cloud, but I think there's a lot of other use cases as well, but that's the one I most feel with, I think. So yeah, I'll just kind of draw this out for you. So most programs and container runtimes, the way they work today is if someone has super user access to your host, it's game over. Obviously they can shut down all your containers, they can take all your shit, they have access to your computer, right? So that's how things work today. And then with Scone or running things in secure enclaves, if someone has super user access, it's not game over, or so that's the promise. So Scone assumes that an attacker has super user access. They have access to your physical hardware still. If you think in terms of the cloud, it makes a lot of sense. They control the entire software stack, right? And you can also run privileged code, you can switch out kernels, you can do anything with the container engine, blah, 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 blah. You can do whatever you want, you're on the host. It's basically a computer. So what this does not cover is DOSes, obviously, but also, hey, side channel attacks of timing or page faults, which that's precious. We all know that now that's kind of sad because there's really not much you can do. But I'll still go over why this is cool, or just there's some interesting designs that they come up with for this that kind of teach about containers, I guess, or why this is a really scary idea. So they had a few designs that they were looking at, and they wanted to keep the code small. So anything that's running inside this secure enclave needs to be small so that if one of their dependencies inside the enclave has a vulnerability, it's not game over. Because if you're already inside the enclave and there's a vuln, you're done, right? So it's kind of if everything is in the sandbox, then there is no sandbox, which is also why you should keep your containers small. And then their second constraint was performance, in that there's just really bad performance with all of this, and I'll go over that. So the enclave thread has to copy the memory arguments and leave the enclave before a system call. You can't execute the system calls inside the enclave. You have to do it outside. So you have to like pass all this shit back and then pass it back over. So obviously that's going to be super slow. And then memory pages for an enclave live inside the enclave page cache. And then after a cache miss, the cache lines have to be decrypted and then fetched from memory. So there's like a lot of things that have to happen. So there were a few trade-offs in their design, and I'll go over kind of what they came up with. So the first one is based on Microsoft's Haven paper, and Microsoft actually deployed SGX integrations into the cloud based on this paper. But since Microsoft's OS is built differently than Linux, this works well for them and not necessarily for Linux or containers, mostly because if you look at this, there's a lot of things inside that trusted layer. And if you remember, like, if everything's inside the sandbox, there is no sandbox. This just like is way outside the scope of what you should be doing for Linux or containers in general inside enclaves. So the second one they came up with is kind of like the exact opposite, where the C library is also untrusted, but then you're passing the syscalls right from this like shim C code outside to untrusted, and any IO call like read or write, you could compromise the data from that call, and then it's just like game over as well, right? So that super sucks. So you can't have it too small inside the base. It's really just like trade-offs galore here. So the kind of compromise they come up with is kind of the same as the other one, but they made this shielding layer so that whenever syscalls are kind of passed into this untrusted host OS, they get like encrypted and stuff. So this shielding layer is just a shit ton of code that like encrypts, IO calls, like read, write, send, receive. They're all shielded, but you're placing a lot of trust into this shielding layer. And honestly, I think the main trade-off here is like, do you trust the code you write, or someone in your company writes this shielding layer? Do you trust that, or do you trust the cloud? And I mean, I work for a cloud provider, so I think you know who I trust. But yeah, it's just an interesting set of trade-offs. And when they did this, they also didn't support things like fork, exec, or clone, which seems insanely hard to run any application without those, but maybe I just run really weird applications, because the threading model inside SGX just like, it just wouldn't work with like the architectural limitations that they had. So you're really, really like shoved inside this box of what you're allowed to do. And it's just interesting. So when they looked at like kind of what happened when they ran applications in this, because they ran like Nginx, memcached, and a few others, SQL, I think. So system calls being performed outside the enclave are expensive, like no shit. You're passing it back and forth, and then you're also having to do this whole like shielding layer on it. So any service that you have that is very like high system call heavy is going to be bad. Surprisingly, memcached is not, so it performed really well, which was really cool, but all the other ones that they tested, it was just a shit show. So then memory page faults have a significant overhead, and then L3 cache misses were really bad too. They were 12 times as slow. And it almost makes me think like if you are trying to do like a side channel attack, it's like if it's moving like Flintstone speed, it might be a lot easier. But yeah, so what does this mean for the future? Like, while this is technically really cool, I'm not entirely sold on it just because of the amount of like code that you have to write to actually get these syscalls to work is insane. That shielding layer for one, and then putting all that inside, the enclave just makes me feel not great about it. And it's just like this weird song and dance of passing syscalls and like threading, and it just, yeah. If you're interested in this, read the paper because it's like it goes into depth. But Azure did turn it on based on their Haven paper, which is a different one. And it's cool. You can play with it in the cloud on Linux or Windows, that other OS. So yeah, that's kind of cool. But is it even worth it? I don't think so. It's such a performance pain. You have to write all that code, and then you also have to trust that code versus trusting, your OS or cloud provider. Or, and honestly, if you have so many trust issues, maybe don't use the cloud in the first place. I'm not sure. So, and it also won't protect against Meltdown or Spectre, so that's funny. Back when I read this paper, that was not even like a concern to me, but I just thought it was funny that one of the one things that it doesn't protect against are side channels. Okay. So yeah, moving on to our last topic. And this is what I'm currently working on at Microsoft for like the open source Kubernetes project. And if you're interested in this at all, we have a working group for the open source project, and we meet like every other Wednesday, and we have Zoom calls, and we're super nice, I swear. Yeah, so multi-tenancy is a thing that a lot of people want. So we thought that like as part of this working group, we would define kind of the levels of multi-tenancy. Because right now, like there is no guarantee with Kubernetes that we support any sort of multi-tenancy model. Like we could, which is the point of this, but we need to define it and then have some sort of guarantee around like what you get and what you don't get. And then testing as far as making sure your cluster is configured so that you aren't, accidentally setting one flag that you shouldn't be or something like that. So soft multi-tenancy is the first type, and this is more like if you have multiple users inside the same org, and you trust them, you trust them not to be malicious. You could have bad actors like someone, leaving the company, and they're like, I'm gonna go delete Donald Trump's container. But yeah, it's not necessarily the same threat model as others, and like users aren't really actively malicious at all. It's mostly for like preventing accidents, right? Like you're not gonna delete your coworker's container, hypothetically. Or try to hack it from your container by breaking out. So hard multi-tenancy is kind of the more interesting one. And this is where you have multiple users from various places in the same cluster, and none of them are really trusted, right? It assumes everyone in the cluster is potentially malicious. Like you're just running bad dudes containers all day, and you don't know what to do about it. So in the case of Kubernetes and a lot of orchestrators, like you have to think about a lot of things, and it's not just the orchestrator that you are thinking about. You're thinking about everything under that as far as what could happen, mostly because we build on all of those things. So when I was laying out like my design for what I thought hypothetically we should do, and this is all in the design doc that I linked in the first slide, and I'll link to these. You start with like the base layer, right? So that would be the host OS. Technically you should start with the hardware and maybe do something without speculative execution, but we're confined to what we have. So the host OS, you're gonna wanna use something like one of the really nice container OSs like I did on my desktop, where you're forced to run everything in containers. It's a really minimal base, and they have like really nice security features there as far as auto updates and stuff like that. And then as far as the container runtime goes, depending on your threat model, there's two ways to go about this, right? So if you're just executing any arbitrary code and you have no idea what they're running, I would consider using the Glasshouse VMs, and only because if they want to run something privileged, right, that we don't allow in our defaults, like you're going to want a VM for that then. But if it's something where you can, sandbox it in ways that you feel great about it, then go right ahead. I personally would do that too. I think it's fine. So network, there's a lot to do here. Mostly like the tools that Kubernetes gives you are really nice. So you can just set a default deny all policy for ingress and egress. So you start from literally shutting off the world to everything. And then from there you build up explicitly what network communication you want between containers and pods and all that. So like just start from no and then go slowly to yes, based off actual code being validated that allows these things, and make sure that it's not malicious. DNS is interesting, mostly because if you're familiar with Kubernetes, we have this thing called kubedns, and it's like service discovery, and it's really cool. But like you want to make sure that your DNS is actually namespace just like everything else. So each tenant inside your multi-tenant cluster needs its own kind of service discovery, DNS cool shit, or just turn it off entirely, because I'm not sure those features necessarily even come into play here, depending on like what type of SaaS or like platform as a service you're building on top of this. But one way to do it with Kubernetes, if you're familiar, is that you can run kubedns, that thing, as a sidecar, and a sidecar is just a container that runs in a pod with everything else, so it shares that same network namespace, PID namespace, and then you're making sure that, no other tenant can, just guess maybe one of your services. So authentication and authorization come into play too, and we have a lot of things for that in Kubernetes. The best one is RBAC. And depending on what you're building, like the main use case that we were seeing for this internally was for a SaaS. So we were running a trusted API on top of Kubernetes API, on top of other things. You just need to know like what exactly your requirements are here to know what you need and what you don't need. But there are tools for going about this, so that's nice. And then you want to make sure that your master and system nodes are isolated. So like things that are running these containers with potentially malicious code needs to be separated from your master, which also needs to be separated from your system services. So like etcd is our key value store for Kubernetes. Like run that on machines that are not the ones obviously running malicious code, and isolate all these from each other so that just the agents running the code have only that. And that ensures that like the means of communication from master to agent are also not compromised. So then you also want to restrict access to host resources, obviously. But so out of the box with Kubernetes, like you can do things like use a host path for volumes and stuff like that. So, and there are tools for locking that down via a pod security policy. These are all just abstractions, but they just like deny, mounting anything on the host. And you can also even shut down, containers from saying, I want to use the host network instead of using a network namespace, or I want to use the host PID instead of using the PID namespace, or I want to use the host IPC instead of using the IPC namespace. You shut down all that because you don't want them to have access to anything on the host. And you can also define in those policies like whether you want the pods to run as privileged or not. So if you are doing obviously sandboxing of containers, you would want to say no privileged anywhere. So yeah, there's also a bunch of tools for that. And then everything else is just making everything dumb to its surroundings. So like back in the day, like when I worked at Docker, there were a bunch of like features requested to make containers more aware of themselves, like inside the container. And I was always against them because I like my containers to be dumb. Like I just don't want them to know about themselves. I don't want them to know about other things. I would love it if they were just like the things and nobody knew what was happening. Like I don't want a container ID inside the container that people could then maybe use for other things. I don't know, you never know. So I just like to think that making sure that inside that container everything is dumb is good because then it can't get knowledge about anything else in the cluster, and then you can't accidentally shoot yourself in the foot and not turn off something like that. So right now containers are dumb and I like it. So yeah, to sum this all up, because that was a lot, containers are not real things. Maybe they should have been called boxes. I mean, I kind of am a fan of that now. Definitely the VM containers should have been called glass houses. Trying to make that a thing. Naming things is super hard, but at least like you can't blame us for serverless. So that one's super stupid. But like in all seriousness, containers with sane defaults are sandboxes. And when you turn those defaults off, you are getting what you asked for, so just be aware of that. And securing containers by default was just like one piece of like a brighter future. So like if we were to apply these same principles from sandboxing containers like I tried with programming languages and other layers of abstractions and user space, then we'll have a more secure user space. So I think like learning from the past and applying it to the future would be really good here. So hopefully this lived up to so bad that it's good. And that's all.
token of our appreciation.
Thank you.
Very much for coming and joining us today. Just for
Thank you so much, Jess. It is now time for morning tea. I did want to do a quick announcement. If anybody has brought luggage with them today and needs a safe-ish place to store it, you can leave it with our rego desk. All care, no responsibility, etc. But it may save you a trip to lockers that are further off-site, etc. There are two important things you need to know about that. The first is that the rego desk will be closed during lightning talks and conference close, so make sure you pick it up by afternoon tea. Or you can pick up your luggage after the conference, but promptly before 5:30, because we'll be closing the rego desk off and packing up by then. And without further delay, thank you very much. Thank you, Jess. Another quick round of applause for Jess. And have an absolutely amazing last day of LCA. Thank you very much.